Hello, in this clip I am going to introduce the fundamentals of feedback control to you. If you were to start with the assumption that we do not know too much about feedback control and ask ourselves what do we mean by feedback control or more generally control, one would probably conclude that to control something is to get it to do your bidding, and that is precisely also what the objective of feedback control is. You want a system to do your bidding, and in this course as I outlined earlier, we are focused with single input single output systems. So, in the context of single input single output systems, what we mean when we say that we want it to do our bidding is that if we provide a certain input waveform, let us call it reference R of t, then we want the output of the system. So, R of t is some reference waveform that we want to feed to our system. This could be any physical system that is of interest to us. It could be a motor, it could be a car, it could be an airplane, it could be a chemical plant. R of t is something that you want it to track. So, the output of the system, which we shall call x of t, should ideally be equal to R of t if we have designed our control system very well. So, this is the ideal, this is the goal of all control engineers, to get the output of the system to track our reference. Now, what is our system? As I said, it could be any dynamic system. So, depending on the particular discipline that we are talking about, the physical appearance of the dynamic system might be different, but fundamentally from a mathematical perspective it is a single input single output system. So, there is a single input u that you can provide to the system, and in response to u of t you get an output x of t, and the relationship between u and x is characterized by a certain input output mapping, which we shall represent by means of this function f. So, this function f could possibly include derivatives of output with respect to time and so on and so forth. So, differential operators and double differential operators and others can also be part of the structure of f. So, the reference I want to track is R of t, the input I am providing to my plant is u of t, and its response is x of t, and ideally I would like x of t to be equal to R of t. How do I do that? Of course, this will not happen on its own. I need to introduce some mathematical function here which manipulates the reference in such a way that when we feed the output of this block to my plant, when that becomes u of t, then R of t will become equal to x of t. So, we should therefore have some mathematical function mapping f1 between R and u which modifies or distorts my reference R of t such that when it is passed through my plant I get it back at the other end. So, what should f1 look like? A moment's thought would reveal that essentially f1 should be the inverse of f. So, if I were to replace f1 with the inverse of f, then you will notice that u of t is equal to f inverse of r, and therefore x of t will be equal to f of u, which will be equal to f of f inverse of r, and that is therefore equal to r. So, in essence all the controls problems can be reduced to this one simple mathematical goal of obtaining the inverse of the system that we are trying to control. So, the system that we are trying to control is called the plant, and the goal of all control engineers is to get the plant output to be equal to some desired reference R of t, and that can be accomplished by inserting an electronic system that inverts the model of the plant and cascading that with suitable actuators to get x of t to be equal to R of t. So, there is this very simple objective that guides the work of all control engineers, both control engineers who use feedback control as well as those who do not use it, and that is to invert the plant. as simple as this objective looks, there is a catch. It is not always possible to invert the plant, and indeed we will see that it is almost never possible to perfectly invert the plant. But apart from that, there are a few other restrictions as well. For one thing, we need to have f to be an accurate mathematical model of the plant. F should accurately represent the plant dynamics. I make this statement to point out that ultimately when we write down an equation to determine the input output relationship for a physical system, that equation is written on the basis of some assumptions. We make simplifications, we ignore terms that are not very significant, and so on and so forth. Now it is assumed that we have been careful in doing our simplifications and ignoring some terms, in that the final output of the mathematical model is almost equal to the actual output of the physical system. So that is one prerequisite for us to be able to invert the dynamics of the plant reasonably well and to get x of t to be equal to r of t. The second condition is that f inverse should be realizable. And this we will discover is a very big condition. So as simple as the problem of control appears, these conditions of f being able to accurately represent the plant dynamics and f inverse being realizable become major roadblocks, especially in the context of feedback control. And the third condition is that u should also be realizable. The control effort u, which is equal to f inverse of r, should be realizable. So to give a practical example, if the input u is so large that your actuators cannot generate that magnitude of control effort, then even though it is possible to compute mathematically f inverse of r, physically it may not be possible to realize f inverse of r. So u should be realizable, f inverse should be realizable, and f should accurately represent the plant dynamics. These are the basic prerequisites for us to be able to get x of t to be equal to r of t, which is the goal of all of control engineering. However, as I discussed, this requirement that we simply obtain the model of the plant and invert it is deceptively simple. Let us illustrate this by means of an example. Let us consider, for instance, a first order system, and let us take the example of an oven and assume that it is governed by first order dynamics, and therefore the relationship between the input applied to the oven, which could be in terms of voltage or current or fuel or whatever, to the temperature rise is governed by a first order differential equation. Let us say the differential equation has the following form: tau s d capital T by dt plus capital T is equal to k times V in, where V in represents the input voltage and tau s here represents the time constant of the oven. So if you provide any step voltage input, then it takes some time for the response of the system to reach its steady state value, and that time is characterized by the time constant tau s. So the first order response of this system to a step input would look something like this. So if this is a step input V in and this is time, then the response of this oven might look something like that. And we see that the response does not really track the reference, and hence we need to invert the dynamic model that we have here for us to be able to track this reference perfectly. Let us attempt to do this in the Laplace domain by first obtaining the transfer function for this system. So it is evident from this time domain representation that the transfer function of this system would be something like this, namely that the Laplace transform of temperature T divided by the Laplace transform of the input voltage V in is going to be equal to k by tau s times s plus 1. So, this is the input output relationship for this particular plant. So, I shall write it out here. The input is V in, the output is the temperature T, and the transfer function is of the form K by tau s s plus 1. The subscript s for the time constant tau is intended to denote the fact that this is a slow system. Most thermal systems such as ovens and so on are slow. Therefore, if I were to provide a step input to this oven, it takes quite some time for the temperature to build up and reach its steady state value. Hence, we have denoted the time constant tau with a subscript and called it tau s. Now, if we want this oven to track a certain reference R, so let us draw this reference R here, and we want the temperature T to be equal to R, what do we need to do? Ideally, what we need to do is to insert a transfer function here that inverts the plant. In other words, we should have a transfer function of the kind tau s times s plus 1 divided by k. However, we note that there is a problem in this transfer function, namely that this is a non-causal transfer function. The degree of the denominator polynomial is 0 because there is no term in the denominator of this open loop controller transfer function, and the degree of the numerator polynomial is 1, and hence it is not even a proper transfer function, let alone being a strictly proper transfer function. So, therefore, we see that even for the most simple case of a first order plant, it is not possible for us to perfectly invert its dynamics. What can we do instead? Is this the end of the road for us? Actually not. We can do a little bit to improve matters and invert the plant's dynamics approximately, if not exactly. In order to do this, let me choose the denominator polynomial of this same controller, which at this present moment cannot be physically realized, to be of the kind tau f times s plus 1. So, let that be the denominator of this controller. Now, the numerator degree is 1, the denominator degree is 1, and hence the controller transfer function is a proper transfer function, and in principle we can realize this transfer function. So, if we now look at the relationship between the input and the output, we note that we would have the relationship to be given by T is equal to K by tau s times s plus 1 times tau s times s plus 1 divided by K times tau f times s plus 1 times the reference R. So, what does that tell us? That tells us that T is equal to 1 by tau f times s plus 1 times R. Now, if we choose the time constant tau f to be much smaller than tau s, then the time constant associated with the temperature rise for the certain input command R of s is going to be much lesser than the time constant associated with the temperature rise for the original oven without any control. So, if we were to plot the step response of this new case where we have this controller cascaded with the original oven, the step response would look something like this. So, the time constant tau f being much smaller than the time constant tau s, the step response rises much faster and settles down close to its steady state value much faster than for the original oven. Now, if we compare the step input and the response, we note that the response is much closer to the input in its appearance than the original response was, and hence we can conclude that we have succeeded in approximately inverting the dynamics of the plant. So, we see therefore that although at the end of the day all control problems can be boiled down to finding out inverses to the dynamics of the systems that we are trying to control. Even for the most simple case of a first order plant, we cannot think of a plant that is more simple than this. A plant that is more simple than this is a simple proportional plant, and that is a trivial case. So, beyond that, the next simple plant is a first order plant, and even for the first order plant, it is not possible for us to come up with an exact inverse for the dynamics of the plant. We can only come up with an approximate inverse and make the response of the overall system relating the output to the input to track the reference much better than what the original plant could, but it is not possible to get it to track the reference exactly. Now, these problems only get exacerbated when we are dealing with plants of higher order, so second order, third order and so on, and even worse when we are dealing with plants that have nonlinearities or that have parameters that are varying with time. So, for instance, if you were to consider another system whose mathematical model that relates the input and output looks something like this: x double dot plus bx dot plus kx times 1 minus x square is equal to u, where u is the input and x is the output. Let us assume in this case that we know the coefficient b and k very well, then we know everything about the differential equation. So, we know the input output relationship very well, but how does one invert this relationship? That is not clear. So, even though we know f that relates x and u very well, we do not know how to compute f inverse that relates r and u, and therefore, we are still stuck with this problem. So, in the first example we could obtain the inverse, but that inverse could not be perfect. In this particular example, we are able to model the system very well, so we can realize f very well, but we are not able to realize f inverse. So, it is in this context that we shall explore a slightly different and interesting technique to invert the model of the plant. So, let us say we have our plant f, which represents the mapping between the input u and the output x. Our goal is to somehow get it to track a reference r of t. Somehow we have to get x of t to be equal to r of t, that is our objective. Now, we shall approach this problem in a slightly different way. We shall first make a copy of the plant. So, when I say a copy of the plant, we are coming up with a mathematical model whose input output relationships we are computing using an electronic circuit or a computer or some such method. So, I shall call the input output relationship of the copy as f cap. Ideally, we want f cap to be equal to f, but if we do not understand the dynamics very well of the actual system, then there will be small differences, and to underscore the fact that there is likely to be a difference between the output of the actual plant and the output of its mathematical model, I have called this f cap, and the output of this model is z. So, both of them are given the same input u, and ideally both the outputs should be identical. Now, in order to get x to be equal to r, what I shall do is compare the output of my copy with the reference r. So, I shall compare them, in other words take the difference between them. I shall do z of t minus r of t, and in the ideal case we want that error e between the two to be 0, because we want the output of the plant to be equal to r of t, but then that is not going to happen naturally. We have to distort this error in some manner using some function h, and what our quest now would be to investigate the general properties of h that will allow the output of that, namely u, to invert the model of the plant. So, what kind of functions h do we need to choose to get x of t to be equal to r of t? If you look at this block diagram, it is reminiscent of a feedback block diagram, but this is not a feedback system yet, because we are implementing all of this inside a computer, and we are therefore not depending on external sensors and other such inputs for us to modify the input to the plant, and therefore this is still what we call as a filter problem. We are coming up with a suitable electronic circuit or a computer based implementation that allows us to invert the dynamics of the plant, and the prototype solution that we are discussing now has this particular structure. Now from this block diagram you see that U is equal to H of E. So H is the mapping that relates the error E to the output of that block, namely U, and E is the difference between R and Z, and Z we know is F cap of U. From this equation we see that R minus F cap of U is equal to H inverse of U, which in turn means that R minus H inverse of U is equal to F cap of U, or equivalently U is equal to F cap inverse of R minus H inverse of U. Now as control engineers, what do we desire U to be? We want U ideally to be equal to F inverse of R. That is what we want it to be. If we choose this as the ideal U, then our x of t will be equal to R of t. Of course we cannot do this ideal inversion. We are hoping that this particular prototype solution will at least help us get an approximate inversion, and we are investigating what properties H needs to have for this approximate inversion to happen. So if you compare what we have got as the expression for U with what we desire as the expression for U, you notice that the actual U will approach the ideal U under two conditions. Firstly, we should have F cap to be equal to F. So in other words, our copy should be a very good replica of the mathematical model of the plant itself. That is one prerequisite, so that I can replace the F cap inverse here by the term F inverse. And the second thing is that if you look at the expression U equal to F cap inverse of R minus H inverse of U, this would be approximately equal to F inverse of R minus H inverse of U when this particular condition is valid. And if you compare this expression with what we desire, we see that we are very close to what we desire, with the exception that we have this extra term as one of the independent variables for the function F inverse. Now therefore, if H inverse of U is a very small quantity, in other words if H inverse of U is much less than R, then what you see is that F inverse of R minus H inverse of U would approximately be equal to F inverse of R itself. And if this is so, we know that this guy is going to be equal to U, and so approximately therefore we succeed in inverting the plant. So the necessary condition for this prototype block diagram to help us in approximately inverting the plant is to get this to happen. H inverse of U should be much smaller than R. What this indicates about the general nature of the function H or the mapping H is that the input output relationship for the function H inverse should be such that the output of the function should be much smaller than the input. Equivalently, what this indicates about the function H itself is that the function H should be a high gain function. In other words, if H inverse is a function whose output is going to be a very attenuated version of its input, then the mapping H should be one where the output of h should be a highly amplified version of the input to that function. So, in other words, h should be a high gain function. What is very interesting about this prototype solution where we have h as the high gain function is that h need not in any way be related to the plant f which we are trying to invert. So, you can choose any high gain function and in principle be able to invert the plant dynamics. However, there is a small catch. So, we have a certain dynamics for this copy here and this dynamics can potentially be unstable, and the concern of instability is exacerbated when you are having a high gain function in the forward path. So, assuming that the dynamics of this copy model that we have in our computer is stable, then our problem of obtaining an approximate inverse to f is done. So, what is interesting about this is that it allows you to obtain the approximate inverse even for plants such as this, for which you cannot directly compute f inverse. But the application of this is even more general. So, suppose we had the differential equation to be of the kind x double dot plus b of t times x dot plus k of t times x times 1 minus x square is equal to u. Even for such a situation we can employ this particular prototype solution to obtain the inverse and get the plant to follow the reference r of t. But there are occasions when these coefficients b and k are not known very well, and it is in that scenario that this prototype solution, this prototype approach breaks down, and that is because in order for this entire strategy to work, we need to have an accurate copy of the plant dynamics. Now, when our plant model changes in time and in a manner that we cannot easily predict, then we do not have a good enough copy at all times t for the plant model. This is one circumstance under which this breaks down. There is one other circumstance, namely when we have uncertainty associated with the environment in which the plant operates. Mathematically what that means is that my plant is afflicted by a disturbance d of t, and if I can measure d of t, I can incorporate that measurement also in my copy and eliminate its effect. So, this can be x, this can be z, I can eliminate its effect using the same technique. However, if I cannot measure d of t, so if this cannot be measured, then this particular approach will not allow me to compensate for its effect. So, it is in this context that as good as this prototype solution is, we cannot invert the plant the way we would like it to be inverted. So, the solution to this problem is to replace the copy of the plant by the actual plant itself and the copy of the disturbance by the actual disturbance itself, and for that to happen we have to invest in a sensor, so that instead of measuring z or instead of looking at the variable z, we directly look at the variable x itself. So, if you invest in a sensor and measure x and implement the same prototype solution, then you will be able to invert plants whose parameters might change with time in a manner that we do not understand and which might be afflicted by disturbances that we cannot measure. And this approach to inverting the plant is called feedback control, and this we shall look at in greater detail in the next clip.